Welcome to Programming Language course, Chapter 5, Target Machine Architecture. Instruction Set Architecture. Instruction set is the interface between software and hardware. Above instruction set, we have high-level language, assembly language, and we have machine code. And then the machine code being organized as instructions. And then those instructions got executed by the hardware. So when we develop a computer system, we will have a complete system like this. But we're starting with a instruction set architecture. And we need to develop that first. After that, we use a simulator on the existing machines, such as the Intel processor, to help you to simulate the machine architecture. And then we build a bootstrap BIOS or basic I/O unit so that we can start to port some program onto the architecture to run. And then we develop a compiler for that instruction set. And then we build the hardware to support that instruction set. After that, we build operation system using the compiler and then working on the basic I/O unit as well. After that, we build a assembler and then compiler of the real machine instead of on the simulator. And then we develop the high-level language such as Java language based on the C compiler. And then we build the application program, and then we remove the emulator part. So that's basic flow for developing a programming language and a computer architecture, and starting from instruction set architecture. And here we have a figure for 15.2, the syntax tree and syntax table for GCD, greatest common denominator. And this is, excuse me, and this is borrowed from chapter 15.2. The reason why I'm mentioning here is in the previous 3-4 chapter, we cover basically the front-end compilers. And then in this chapter, we basically cover the back-end compiler and then the instruction set architecture. And in chapter 15, actually, it will cover the back-end architecture. And then the program for GCD has such a syntax tree will eventually be built based on this simple table. And then this one will be used to generate the instructions. And those instructions is for machine code. So the simple table here will work as an interface, and it may be mapping to the instruction one by one or one by a group. So the control flow graph for the GCD will be like this. Code within basic block is shown in the pseudo assembly notation. So here it mentioned it is pseudo assembly notation. So this is almost like can be mapped into instructions one by one, and it is in the control flow graph CFG, and we actually mentioned this in chapter 4. And so this is ready, almost ready for the code generation, and we talk about this to the SSA, static single assignment stage, and then go into optimization, and go into SSA, and then go into instruction register allocation. And that actually need to have the instruction set architecture information to support that. So this chapter we focus on this, the instruction set architecture and its relationship with the front stage compiler and back stage compiler. So chapter 5 and chapter 15, these two chapters are here in this book to for the back-end compiler issues. And in chapter 15, it's more on the compiler issue. From gimbal, SSA, optimization, and SSA, RTL, assembly, generation, and machine code generation. And this chapter 5 is more dedicated to ISA, instruction set architecture, memory coherence model, loop level optimization. So here is talking about the machines and your intermediate code to the optimization for loops. And then more systematic introduction for the backend issue for compiler is in chapter 15. And here we just provide the background information, especially the ISA architecture. So computer architecture and programming language. Computer architectural issue that impact programming language in many aspects. It will be related to the code generation, platform dependency, multi-threading, and multi-core. A few topics. Code generation largely depends on the instruction set architecture and the parallelism available to be explored in the machine in the code. So we talk about this instruction level parallelism, 6 over risk. And in chapter 6, we will cover some loop unrolling for pipelining, and then different architecture, the superscalar, the scalar instruction, superscalar instruction, VLIW instruction, and then platform dependency issues such as virtual machine, interpreter, native code compilation, and then concurrency that will be covered in chapter 13. And finally, the multi-core. But multi-core issue will not be, we actually won't spend too much time on this multi-processing. We will start at this chapter 13 for multi-threading. Even though the i8 core for Intel has already almost released, and then it will cover 6 cores. Current i7 has 4 core, 4 processor core, and then i8 has 6 core. Even though that this topic is very important, but actually is actually not directly linked with programming language. It's more related to operation system. So here we actually spend more time on the programming language aspects and discussing the programming language and its relationship with computer architecture. Programming language and compiler design. To take advantage of instruction level parallelism, so we try to explore, So we try to explore the instruction level parallelism to optimize the code optimization for backend, and then vector processing and task level parallelism. This task level parallelism is in chapter 13. Here we talk about instruction level parallelism. So single instruction, how can we optimize it? And one by one, how can we optimize it for loop unrolling? And then chapter 13's part is like, I will have forking, join for different process. That's process level or task level parallelism. So we mainly cover these two in chapter 5. And the backend optimization may or may not related to this. depends on the support for compiler. So here first, before we go into more detail design for computer architecture, let's look at pipelining. So on the left hand side is unpipelined process. So you start to have a RAM, and then your CPU. Actually, this one we call it. This one we actually call it Datapath. You start to get an instruction from the memory and get it to your fetch unit, and then that instruction got decoded, and then it started to execute. So it may send the instruction to do a load data from memory to register, or maybe get data from register and compute with two register and provide the result, maybe right back to memory, maybe right back to register, maybe do nothing, maybe only jump the instruction, jump the code, and then change the program counter. So that's the basic operation for this one is a CPU. Well, CPU may not include the RAM. It would. It actually will have some SRAM on chip, or maybe some cache on chip to support. And off chip you have DRAM. So that's a CPU, but this one is an unpipelined version. And on the right hand side we have pipeline version. And pipeline version compared to this non-pipeline version basically had the following feature: uniform clock cycle. And then it divided into several stages. And this one is unstaged. The instruction may have different execution time. This one is a cycle-based design in pipelining. So each cycle we do something. But this one may not be following the clock. But with this uniform clock cycle, and then optimize the optimized data path, we try to achieve higher level of the instruction level parallelism among the instructions. So because of pipelining, we introduce a few ideas. First, the register file and caching, and then pipelining and multiple stage and uniform clock, and then also related to the caching, how to improve cache. So this one is around 1985 when RISC machine is being developed. We start to have the pipelining, deep pipelining. And one of the important issues is to optimize the memory hierarchy. The reason is if we can optimize the operation, everything on chip, especially just on the register, because it is actually just 0.2 or 0.5 nanosecond. Say I have a CPU of 5 gigahertz CPU, the clock cycle is just 0.2 nanosecond. Then using my register will provide best performance. And anything below will be slower, get slower. So we would utilize the register the most. And then everything below is trying to beef up the data in the register, trying to make the register busy. but provide different level of caching. And because of caching, we need to introduce the virtual memory idea and snooping bus idea to support the good caching. And good caching is to buffer the data inside your CPU, so we will make sure our registers has the best copy of data that will keep CPU busy without wasting time on waiting for the I/O or memories. So here, the access time and capacity is based on the 2015 technology, based on from the textbook. And register access is within a single clock cycle. And something like caching, maybe 1-2 cycle, of chip memory I/O maybe 20 cycle. So the lower you will spend more time to read data, and it take longer, more number of clock cycle in order to achieve it. So we don't want our CPU to be halted to wait for those memory I/O. So we need to have different level of caching and memory hierarchy. So we keep our CPU busy, but if there's a data miss, we fetch on the lower level to support the memory calculation. Pipelining. Pipeline is depending on the instruction level parallelism. So on the right-hand side, we have the pipeline stages. So typically, a CPU design divided into the following stage: instruction fetch, then decode, and then execute. And then this one, MEM, is memory access. And then the last one is write back stage, write back. So basically, you get the instruction, you decode it, you execute it, and then you get data from the memory, and eventually you write back the result back to memory or register. 5-base stage, but not every CPU have this 5-stage architecture. They may have a minimum of 4 stage, and maximum have maybe 8 to 9 stages. And we actually can interleave the instruction in such a pipeline stage, so that if we run long enough, our parallelism will be almost close to a degree of 5. So basically, if we have 5 stages, we will keep our CPU busy like this. So the parallelism in general, if you cut the off head, it's almost like 5 instructions in the clock cycle. So you almost achieve a parallelism of degree 5. But the problem is not the pipelining not always on the full capacity. So if you have a degree of parallelism of 5, if you can maintain the CPU to run the parallelism on over 3 plus, probably good enough for the pipelining. So here on the left-hand side, we have comparison for an instruction for a single clock cycle. We have low store, and then we will waste our time. And then we have the pipeline implementation. And here is the multi-cycle implementation. You can finish one instruction and then the other instruction. And in pipelining, we can actually get one instruction initiated per clock cycle. Superscalar. Superscalar is another way of enhancing the degree of parallelism. What is superscalar? Our pipelining is just one instruction per clock cycle. So we actually maximum can achieve the degree of 5 in parallelism. But if two instructions don't have the data dependency among themselves, then we can actually fetch two instructions in one clock cycle. What are these instructions that can be allowed for this? For example, one is to move from register 1 to register 3. The other one move from register 2 to register 4. These two can always be in parallel because the two instructions have no data dependency at all. These two we can actually fit into one superscalar stage. So basically we fetch two instructions at a time, and then based on the dispatch unit, we may send to different execution unit. So here we have two integer unit and one floating-point unit. So you still need to depend on the hardware resource in order to optimize for the superscalar. For example, if you have two floating-point instruction, but you only have one floating-point execution unit, then the superscalar will not be available. You need to squash one of the instruction out. You can only allow one if your hardware doesn't support it. So the number of instruction unit and floating point unit will actually decide how much superscalar you can afford. And not only superscalar, we can also achieve the super pipelining. What is super pipelining and what is pipelining and what is superscalar? We show this basic pipelining, and this one is a 4 instruction stage 1, and we can make it each time it fetch 2 instructions to achieve superscalar. We talk about this. And the other one is, well, I have 4 instructions cycles, but can I further break down to a half cycle to initiate one instruction? So basically, you may have one instruction fetch stage, but you divide it into first half and second half. Because usually in the instruction stage, you have one arithmetic operation, the other one is to do data latching. So that provide possible super pipelining that improve another degree of 2 improvement in parallelism. So if, for example, you have 4 stages in pipelining, you will have 4 times 2, totally 8 level of the pipelining if you use the super pipeline architecture. Of course, you need to be making the cycle 1 and half cycle, first half cycle and second half cycle more balanced in order to achieve higher level of parallelism. And the fourth parallelism mechanism is very long instruction worth. What is very long instruction worth? This is different from the superscalar. Superscalar is the 2 instructions at a time, but this very long instruction worth is I make my instruction super long. So I put many operand in there and many operation in there as well. So inside one instruction, using one clock cycle, I can execute multiple data for different register. And then I provide multiple integer unit, multiple floating point unit, multiple load store unit. This LD and ST is load and store. So basically each instruction you have, for example, you have plus, minus, and multiplication. Those are instruction unit. And if you have operation for floating point, it will be operated on the floating point unit. And load store is you need to write back to memory or load from memory and load to the register. So this is another way to improve the parallelism at the instruction level. And sometimes you still have data dependency among the instruction. So we can steal some more clock cycle to improve the full utilization of the CPU to allow the out of order execution. So if we have the regular ordered completion, we have these three instructions. We do it one by one, but somehow instruction one have a using the R1 as a pointer to fetch some memory. So the next two instructions may be waiting for it to finish. So it causes the clock cycle loss. So what we can do is like, I don't need this instruction 2 and 3 to wait for the load store unit because they are not related to load store unit. So I allow the this first instruction to continue to wait for the memory access unit clock cycles, and then my 2 and 3 can finish first. But all that will actually depend on whether these 2 and 3 will depend on the result for the memory access or not. If so, then we can use the out of order completion or execution. So it depends on the data dependency for this out of order execution. Out of order execution microcode. We can actually not using the instruction, but further decode it into microcodes. And in microcode, we can even achieve higher order of the parallelism by utilizing the out of order execution. So for example, I have a move register 1 to register 2. Then I can further break down to get R1 and then enable bus and then write register 2, something like that, some microcode. And this microcode I can actually put into the brain some microcode memory and then improve the parallelism when we dispatch the different instructions to improve the out of order execution. The next topic is the reservation station and execution unit. The reservation station is related to the renamed op. So we have the renamed op, so we can swap the register number decided by compiler at runtime. So you need to reserve for the reservation for each register. We call it a reservation unit. And because the instruction is out of order, so after execution, we need to have a certain unit to reorganize the instruction. So make sure you can maintain the data consistency after the execution. So here is a typical simple pipelining with multiple execution unit. And here we have another one that we provide some queue so we can issue a lot of microcode. Right back, we have a sync point, so it will support the possible out-of-order operations in more efficient way. So we have the decode to make sure that the out-of-order execution with the reservation station can make the pipelining more efficient. So multi-core operation, we may have multiple CPU, multiple thread operating on it, and each CPU core has its own instruction cycles. So this is for the task level parallelism using multiple core. And this one actually is not backend compiler issue. Actually, it's a programming issue, concurrent programming issue. That's a different level of parallelism, and it's not discussed in this chapter, but I just want you to know that parallelism is one of the goals we try to accomplish in the generation of the backend compiler code. But the problem is, this is not the only way to optimize the code. We can also optimize the program by providing multi-core processor and not need the operation system to manage the thread. The thread may be in one CPU, it may be in multiple CPU. In one single thread machine, it will be executed like this, even it's time shared. And then multiple core, you will have achieved higher order of the parallelism and provide better performance. So concurrent programming also can be done in timeshare format or pipeline level or multiple core level. So here is the chart for concurrent programming. For multi-threading, we have a same memory, one virtual processor. So actually, it looks like you have a multiple processor environment, but in fact, it is only one. These virtual processors are time shared. So in that case, we call this multi-threading. Multi-processing is that we actually have multiple processors, so we have these process load on different core. And maybe not all at one time, but sometimes depends on the CPU you have, the number of core you have. You can actually do parallelism to run multiple processes at a time. And this one is the Datapath design style. We have basic form, that's basic form, and then we have pipeline design, and then we have superscalar, and then we have VLIW. So different design style, the data paths are different. And here I actually borrow a slides from a Japanese article. So you'll see there are some Japanese language over there. And then this pipelining, this pipelining can have the superscalar format, and then out of order transformation. So basically, pipelining, you have superscalar pipelining super pipelining. This is superscalar. You have superscalar. You have hour order execution, and hour order execution you can actually this actually is instruction translation. You can have real IW or this one hour order execution. Two possibility, two candidate for hour order execution. I'm sorry, the instruction translation. And this instruction translation actually means the microcode decoding. You provide a microcode, you break down the instruction to microcode, you actually can achieve real IW and auto order execution. And this requires a translation for your instruction. So the database design depends on how you explore the instruction level parallelism. You have the pipelining, superscalar, super pipelining. This one super pipelining. Superscalar is over here. 1, 2, 3, 4, 4 different five different design style for the Datapath. The next one is the assembly level view. The assembly level view is that get started from the source code. We have a source code x equals x minus 15. Then we have a parser. We generate the syntax tree like this, and we are ready to generate the intermediate code by the CFG, the control flow diagram graph. And then we do high-level optimization. We generate the code as intermediate code, and then we actually optimize it, and then we have the assembly code, and then put into the assembler to generate the machine code. And here we compare the assembly and target code for C language. So if we have a C code, we feed into C compiler, it will generate the object code. And assembly, the same thing, we use the assembler, it will generate the object code. And in fact, this object code we can link together to run together. So it can be from C language, can be from assembly language, can be from C++ language. And we can all start it from the source code, compile to pre-process to some .C code or something, and then use C compiler to generate assembly code, and then link, generate the object code, and then link them together to run. So you can think about the assembly is one format of the intermediate code. So in Java environment, we have the source code, we have the bytecode compiler, and we generate bytecode, and then we actually have the native code for different machines. That's just-in-time compiler for bytecode interpreters. For C language, we have source code, we have different compiler, they generate different executable code, and some of them sometimes you may generate with different object code and then link them together. And here we have the C code pass through compiler, and you may generate assembly code, and then you can have the generate into machine code to run. Here's one instruction set architecture. So we transform the high-level language to some language. Actually, it's like Gimpo style, and then we generate the assembly code. And the instruction set it will be something like this. You have opcode, you have the memory HS mode, and then you have the registers. These are the instruction set format. And your assembly code can be assembled to machine code and then load into a machine to run. That's the object code, the object code format in text format. Assembly level view. As mentioned earlier in this course, a compiler is simply a translator and translate a program written in one language to another. The other language can almost anything. But most of the time, however, we talk about machine code. Assembly level view. As a review, we will go over some of the material most relevant to language implementation so that we can better understand what the compiler had to do with your program. So we will discuss the relationship of compiler, machine, and the programming language, and why certain things are fast and some are slow. It may be because of hardware resource limitation, maybe because of the program algorithm. And why certain things are easy to compile and others aren't. We want to figure out what are the limitations. Assembly level view. There are many different programming languages and there are many different machine languages. Machine languages show considerably less diversity than programming language. Traditionally, each machine language corresponds to a different computer architecture, but nowadays, because of the bytecode, it's hard to say. The implementation is how the architecture is realized in hardware. Assembly level view. Formally, an architecture is the interface to the hardware, what it looks like to a user writing program on the bare machine. In the past 30 years, the line between these have blurred to the point of disappearing. So it's hard to say now because the line is really blurred because we have instruction decoding or microcode transformation in your Datapath now. So compiler has not to know a lot about implementation of it to do a decent job. Assembly level view. Changes in hardware have made new implementation techniques possible. So to study the computer architecture will help to know what kind of computing model can be allowed, and then you will benefit from the hardware advances. In the discussion below, we will focus on modern RISC machine and with limited amount of coverage on the CISC. Workstation Macro-Architecture. Most modern computers consist of a collection of devices that talk to each other over a bus. For the point of view language implementation, the most important device is the processors. The second important part is the memory. Other devices include disk, keyboard, screen, network, general purpose serial and parallel ports. For this workstation, almost all computers use the monument machine concept. And basically, the process just repeat the 5 stages in pipelines. And this one's okay, I'll skip it. It's a fetch execution cycle. So crucial component of typical processor include a collection of functional units. That is the IPU, instruction processor, the hardware to decode instruction and drive the other functional unit. Second, hardware to fetch instruction and data from memory and to store them back to them. So this is low store unit. So the first one is IFP, instruction functional processor. Second one is low store unit. Third one is ALU. 4 is register file or registers. And the last one, hardware to move the various, so this one is the bus for data communication among the CPU units. in this hour, we'll discuss the data path. What is a data path? And what are the data type in languages? What is data path? The data path is the data flow path that is used to process your data. So basically, you have starting from your RAM, and then you log into your instruction unit, and one by one you do execution, and you have a rule, external operation, and then you have memory access and write back to memory. This is called data path. And on the side, there's a control unit that send all the control code to the data path. And who control the control code? That is your instruction decoder that give the instruction to the control unit. And auto order execution is similar on the right hand side. You have the instruction request and then put into some buffer and then rename the registers and then put it into and that rename of the operation is put into a reservation system, and then you put into different functional unit to help you to process it. And then there's an auto order buffer, and then put them back into order for the instructions. And we provide second level data cache over there. These are two different data paths. So data representation. For ANSIC, we have primitive data type, char or character, integer or int, float, double, and void type. And then derived data type, we have array, pointer, and function. User defined, we have enum, structure, and unum for C language. So basically, in C, we have primitive derived. Derived is basic abstract data type. Some language, some data structure books call these as abstract data type. So these has heterogeneous or homogeneous data type. And that's based on the basic data type. But in C, there's no reference data type or pointer data type. There is a pointer, but there is no objects. So here are the range for each data type, number of bytes. But that's the standard for ANSI, but in the old day, they may be different. And here, for ANSI, they use the 16-bit as integer. But Java, we know, is 4-bit. And then there's a long format for this. But it's actually in newer standard, it has different definition again as well. Data representation for C#. C# is like more like a Java language. You have reference data type for class, interface, data key, and array. Okay, and then primitive data type for integer type, real type, Boolean, and user-defined structure. And that is primitive data type and structure. And then there's a enum type, C#. For Java, you have reference data type and primitive data type. Primitive data type, you have Boolean, character, long, integer, byte, and short, float, double. Reference data type, your class, array, string, enum, and interface. A number of bits and bytes are here. For Python, it's different. Python is on top of C language. So every type of data in Python are just simple objects. So here we talk about a whole hierarchy of data. NumPy. In NumPy or NumPy, actually, it had more different data structure for Python. Memory hierarchy and data representation. Memory hierarchy. Memory is too big to fit in one chip. In fact, this actually right now, as the day we are right now, this is questionable. Now it's possible to put everything in one chip as a single chip computer. But anyway, memory sometimes is too slow, and actually it usually is put off chip. But we definitely need to do a lot of memory transaction. For example, we have integer a equals 3 in Java or C language. Then this actually, if you have a memory location in memory, before you do some computation, you need to save it as 3, and then later we may have a plus b. Then you need to get the data from a variable, that's from this location. Then there's a memory transaction, and there's another, maybe b stored with 4 or something. There's another memory transaction. These cannot be avoided. Before we do any computation, there may be some memory transaction, and if it is off chip, you will spend many clock cycles. So the memory hierarchy in the old days, really old computer, there's only one memory and your CPU. And then since RISC machine, we start to have a CPU and then one level cache and then memory. So cache works as a buffer between CPU and memory. So try to increase the number of levels in memory hierarchy will allow CPU to be free from the memory bottleneck. And we can preface some data from memory to cache to make it faster. So later there's a level 2 cache or even level 3 cache. And also the on-chip register file become bigger. And then level 1 cache may be included into CPU. There are a few different techniques being used to improve the CPU utilization. And most computers therefore employ a memory hierarchy in which things that are used often are kept close at hand. So here we see this chart before. Basically, on-chip register is faster. We try to use register as often as possible. Then level 1 cache, and then level 2, 3 cache, and then off-chip cache, and then main memory. So when you are at the main memory, it's something like you compare to this. It's a ratio of 50 over 0.5. So actually, this is actually a order of 1,000 times, 100 times. I'm sorry. This one, let me see, times 2, yeah, 100 times. The order 100 times slower. But this is an ideal case. You may not be able to always just access to register. So then there is a hit ratio and miss ratio for cache. And in fact, before we use the cache, it actually you will try to register file first. Try to use a compiler to allocate it in a register file first, and then you maybe have level 1 cache, level 2 cache. So code be optimized to access as the register as often as possible, But if it cannot be put into a certain statement such as move from register 1 to register 2, if you cannot do that, then you do indirect access to the memory as a pointer. Then you need to at least access level 1 cache. And then level 1 cache, depending on the size of the level 1 cache. For example, if level 1 cache is sitting K, then when the level 2 cache is of such value, then the hit ratio and the miss ratio, actually this is the hit ratio, will be something like this for sitting K level 1 cache. Level 1 cache, if it is a K, it will be something like this green line. So apparently, right here, the level 2 cache need to be bigger than 16K to make a difference between two level 1 cache size. So actually, at least the level 2 cache need to be actually double the size of the level 1 cache to make a difference. That's a study for hit ratio. If you really want to look into the hit ratio for caches. And hit ratio means when I access the level 1 cache, most of the time I'll get my data over here. And if it continues to miss, then I go to level 2 cache. So if I have a hit ratio of over 90%, that means what? Let's go back to the previous page. That means like most of the commands, I may just spend 2 clock cycles. I may spend about 2 clock cycles compared to register. I will be able to finish my memory access. So worst case, memory access with level 1 cache, 90% of the time, I just need to spend 2 clock cycles if it is access to level 1 cache. And level 2 cache, that's about 20 cycles. If I need to do on-chip access for level, off-chip level 2 cache or on-chip level 3 cache, that's about 20 clock cycle difference. So here is the miss ratio of different individual cache size. So studies show that actually if you want to set a threshold for 90%, then somewhere like about here, about sitting K level 1 cache will be good enough. But that also depends on your benchmark program to analyze what ratio would be an adequate cache size at the level 1 and level 2. It is possible that you build a simulator to predict the miss ratio and hit ratio. Memory hierarchy. Some of these levels are visible to programmers, others are not. For our purpose here, the levels that matter are register and main memory. And that has the logical meaning because they are in the instruction. It's supported by instruction set architecture. Cache is transparent. So registers are special locations that hold data that can be accessed very quickly. It's on chip, and then it's only 1 clock cycle. Within 1 clock cycle, you can finish it. A typical RISC machine has a few set of registers that are used to hold integer and floating point operands. And all of the registers are SRAM cells. Memory hierarchy, it also has several special purpose registers including the program counter. A program counter holds the edges of the next instruction to be executed. And usually, because the instructions are actually stored in the memory at a sequential format, your program is something like this. You keep doing that. So because it's in the sequential format, so the instruction can be loaded to cache block by block. But data sometimes is not accessed in that way. So instruction is more cacheable, and program counter is holding current location for the for the program. And then processor status register that including like 0 greater than 0 flag, a few different flags to represent the status for the processor, and then maybe interrupt indicator. So whole a variety of bits of little interest in this course, but actually help the understanding for CPU a lot, but we won't discuss too much for this. Data representation. Memory is usually byte adjustable, meaning that each 8-bit piece has unique edges. Data longer than 8 bits occupy multiple bytes. Typically, an integer occupies 16, 32, or 64 bits. A floating point number occupies 32, 64, or 128 bits. Here's the computer numbers, integer and floating point number, the hexadecimal digit. And hexadecimal digit actually is only a symbolical meaning that you have 0 to F. But real data stored in computers still be bits in binary format. And the negative number is stored in two's complement format, and I will explain two's complement format later. But a single digit, for every 4 bit can be represented as hexadecimal digit, and this hexadecimal digit also called as half byte because it's 4 bit, and usually you will see that 0A or something that's actually represent 1 byte for 2 half bytes. And then we have the representation for single precision 32-bit floating point, double precision in 64-bit, and for floating point number, it's under IEEE 754 standard. So basically, the number is represented by this. This F also called a semantica. Sometimes it uses the M instead of F. Here I think it try to represent as a fractional number, but usually it's also called a semantica. So data representation. It is simple to know that unlike data in high-level programming language, memory is untyped, just bits. Operations are typed in the sense that different operations interpret the bits in the memory in different. So basically, your integer can be interpreted as unsigned data, signed integer, and maybe the same 32-bit being interpreted as floating point number, or maybe some of them being interpreted as ASCII code using unsigned number. So actually, in computer, it's all bits, but it is interpreted in different format. So typical data format including instruction, integer, and floating point. Data representation. Other concept we will not detail, but covered in other courses, and this including big endian, little endian, but we will mention about this. Integer arithmetic, two's complement, floating point standard. Here is the data representation for big endian and the little endian. Big endian store bit end first. So if we have a number, we have a number DC4, we store a higher order byte in lower memory location. That's big endian. And if we store in little endian, the lower, that less significant byte being stored in lower memory location. That's called little endian. But different processors, say the Intel processor is little endian, Motorola processor are big endian. So for example, a integer, we may have 32-bit, and 32-bit, for example, we have 0A, 04, A3, 59, say, 24 bytes. And then these 4 bytes, we have little endian, we will store memory location 0, 1, 2, 3. 59 will be stored here. It will store like this. So little endian store the little end first. And it varies machine from machine. And sometimes language to language as well. So language with virtual machines such as Java, it is interpreted by language. And the machine effect is hidden. So for Java, big integer is big endian. So it doesn't care about the processor in Intel. It's high. So we have a native core over here. But Java virtual machine is on top of it. And your source code or bytecode would be operating on Java virtual machine in big endian format. But the native code really operate on the little endian format. There is another level of translation. Data representation. Big endian, like this one, we have this number, that will be 00000037. And little endian will store the 37 first and zeros, something like that. So as you can see, little endian stored in the reverse format for big endian. So big endian, you have higher bits, so you actually like this. If you consider that it's like an array, you actually sweep the data like this. And this is 5, 0, 1, 2, 3. And then if you have a little endian, it will be something like this. Processor arithmetic. Why we talk about processor arithmetic? It is actually regarding when you have an instruction that got decoded, and then the next stage you feed data from register, and then you put into a loop, or maybe data from memory, and then they perform summation, subtraction or multiplication with a loop. So that's a processor arithmetic. Help you to understand how the program being executed in the machine level. First, let's look at the conversion of the binary to decimal and decimal to binary. Say we have a number 155. We try to convert it to binary. So the way to do it is I have a 155. I divide it by 2. You got like 77 and remainder 1. And then I divide it by 2. I got 3. And then I have 8, remainder 1. And then I have 38 divided by 2. I got 19, remainder 0. I divided this by 2. I have 9, remainder 1. Divided by 2. I got 4, remainder 1. Divided by 2. It's 2. I'm sorry. It's 2, remainder 0. And then divide by 2, remainder 0. And then last data here is actually 1. So then I read from here to here, I will get 1, 0, 0, 1, 1, 0, 1, 1. If I read from here to here. And that's the number for binary representation for 155. And if I want to convert this the binary number back to decimal, then I just put a weight on top of it and then multiply it and take sum of it. So here is the way to read for decimal to binary. Now let's look at 2's complement. What is really the 2's complement? Because our numbers say we have 4 bits, it started from here to here and then to here. If it is unsigned, the number would be 7, 8, 9, 10, 11, 12, 13, 14, 15. But there is no negative number if we represent the data, interpret the data in this way. Now, if I want to use the, if I want to represent negative number using this 4-bit data, I will cut this into half, and this half I will use as negative number. So the way to interpret it is, if I have a number x, that's a positive number, and I will try to find the negative number for it, I will define it as 2 to the power 4 minus x. If we are using this 4-bit format. If we are using 8-bit format, then we will use actually 8. We will use 2 to the power 8 minus x for 8-bit format, and then same thing for 32-bit, it will be something like this. Okay. And why this work? Why this work? Because if our sum is 2 to the power 4 for 4-bit representation, this number actually is overflow, so it will be thrown away. If you do x and then 2 to the power 4 minus x, they sum together, you will end up with 2 to the power 4 plus 0. This got thrown away because it's overflow, so you end up with 0. That's how we operate it. So we want to use the negative number in this format. But in order to find two's complement, it's hard to understand how it's represented. So we invent a different way of getting it. Is 2 to the power. For example, if we are using a-bit system, this negative number will be interpreted as 2 to the power a minus 1 minus x plus 1. This part is called 1's complement. And the rest of it, this whole thing, is called 2's complement. Now, I would talk about how to find the 1's complement and find the 2's complement. Say first, I have this number in 4-bit format. To find its 1-bit format, I will use 2 to the power 4 minus 1 minus x. That's 1's complement format. And this one, in fact, for 4-bit, it will be 1111 minus your x minus this a. It will be 0100. You got 1011. And if you notice that it actually is a big flip, you flip the bit 0 to 1, 1 to 0. So you actually don't need to do this calculation. You just need to find a number 0, 1, 0, 0, and if you flip the bit 1 to 0, 0 to 1, that's 1's complement. And then you do the 2's complement plus 1, so you actually plus 1. You end up 1, 1, 0, 0, that's your 2's complement. And that's 2 to the power 4 minus x. Now, we have a-bit system, and we have a 79 represented by this, and we do bit flip. That's 1's complement, A1. That actually is 79, minus 79. And if we do addition, if we perform addition for this bit with this bit, it is 0, carry 1. This one, and this one is 0, carry 1. This one, and this one is 0, carry 1. This one is 0, carry 1. And this one is 0, carry 1. And this one is 0, carry 1. This one is 0, carry 1. This one is 0, carry 1. But this one got thrown away. So the end result will be 0 if you sum 79 with minus 79. And Java's special number rule, we actually use the IEEE 754. And Java's character is 16-bit and supporting the Unicode UTF-16. So it's all 16-bit in Java. If you need to, like we call is the multilingual plan, basic multilingual plan 0 is supporting this in Unicode. And floating point number is represented as this. So pretty much the signed integer we interpret it with 2's complement format. Character we interpret as Unicode, and float and double interpret over here. These are the primitive data type in Java. And different language or different machine have different way of interpreting it. And here is binary addition. I believe most of the students had taken the computer organization, so we will skip. Same thing here. And ASCII code. ASCII code is the early days representation for symbols. And in fact, the first two parts, from 0 to 31, is control characters. And then we have the punctuation mark, and then numbers, and then uppercase characters and lowercase characters. But that's only 7-bit. That's the early definition for ASCII. And then later it changed to 8-bit ASCII code. And then later it got merged to Unicode. So that's the transition for character code standards. ISA-related programming language and compiler design issue. We actually look into this because this is related to programming language, including the instruction set choice, the proper processing unit, hardware selection to make it faster, memory access mode to reduce the memory latency, big endian, little endian, not related to code generation, and also, as I mentioned, Java virtual machine have different requirements in the hardware. So either you implement in here or in the native core library to handle the machine. And then also how to dispatch your command to the processor unit. And loop unrolling and superscalar via IW, pipelining, super pipelining, code reordering optimization to explore instruction level parallelism. And language which require programmers work on defining data bytes tend to be faster. So if you can work more low level, it will be faster, but actually it's more tedious to do programming. So here are the impacts for ISA instruction set architecture to the programming languages. Instruction set architecture, number 1. Now let's look at the instruction set architecture. The set of instructions executed by modern processors, including data movement, ALU, arithmetic logic unit. Sometimes we write it as ALU, and it's called ALU. Control transfer, jump call, trap, jump to into operation system, return. So basically, data movement, store, load store, pop, push, move memory, swap registers. 3 types of instructions. 3 instruction type. Logic switch control. First, we have computation that's happening in ALU, arithmetic and logic operation, test and comparison on values held in registers. Second, data movement with load and from memory to registers. So the first type, it all happened on CPU. So it's in the processor, that's the computation. Data movement, you move from memory to the register, that's happening in CPU. Store register to memory. I'm sorry, this one actually, the memory to register is actually from your memory onto your CPU. And this one store is right back to the memory. That's data movement. And then control flow, it actually sometimes is just advance of the program counter. Sometimes also need to access the instruction from different memory location. So 3 different type of instructions. And they have different memory latency. Instruction set architecture, we have different address mode. instruction can specify many different ways to obtain their data. Data in instruction, data in register, data address of data in instruction, address of data in register, address of data computed from two or more value contained in the instruction and or register. So data in instruction, that's the fastest. You even don't need to access the register. Then it's this one. So this one is first, this one second, fastest. And then you have indirect data access. And then this one is actually you get it from register and then it do addressing. And the last one is more longest memory latency. You get two value from memory and then calculate the address of the data and fetch it and go back. So there are different access mode, and different access mode have different memory latency. Instruction set architecture. On this machine, arithmetic logic instruction use only first two of these addressing mode. Load and store instruction use the others. So basically, ALU is very CPU centric. And other than that, you rely on load and store. So we try to minimize the use of load and store because they will increase the latency. And sometimes the load and store can be set apart if our CPU is multiprocessing unit environment. Say we have separate instruction ALU and integer ALU and floating point ALU, and then load and store can be in parallel if they wait for longer clock cycles. The hardware is designed so to minimize the latency dependency. On system machine, all address mode are generally available to all instructions, but typically you need to have one instruction wait for the other. But nowadays, the risk are not much difference because the use of microcode. So here are different addressing mode: register mode, index mode, symbolic mode, absolute mode, indirect register mode, indirect auto increment mode, and the intermediate code mode. Okay. Intermediate code mode is actually for constant and literals. So the word following the instruction contain the intermediate constant n. So basically, this one is also fast. And register mode, you get the data from register content. And index mode, you use the register number plus the index number x, and then point to the operands. So you kind of using the register content and some number to advance to get some data. This usually is used for array. Symbolic mode, you have the program counter plus x to the operands. So this is the relative address from the program counter. And usually this is something like I have a code segment and my program running here. I try to have a relative address to get my data and come back. So it's good for the global variables. And absolute mode. Absolute mode is given the address and then jump to there. Or actually, I access data from there. That's absolute mode. And Rn use a pointer to the operand. That's a pointer type. Indirect register mode. And indirect register mode is increment. This is also good for array or something like array or pointer or linked list. And this index mode is more for index array. And pointer type is usually used for object data fields or structures. here has different calculation of the memory mode and how the instruction being laid out as number of bits. And typical instruction in different group: move, mathematical instruction, multiply, division, add, and subtraction, logical instruction, and or, negation, and equals more, rotation shift instruction, A shift, L shift register, and LSL, bit instruction, bit set, bit clear, bit toggle, and bit test. And then compare, skip, branch, flow control instruction, branch, call function, remote call function, or repeat. Shadow stack operation, push and pop, link unlink. Control instruction, no up, and this reset. DSP operation, multiply, add, and accumulate, and different others instruction. Conditions and branches. All instruction set provide branching mechanism to update the program counter under the program control. Branches allow compiler to implement conditional statement, subroutines, and loops. Conditional branches may be controlled in several ways. So if we have A assigned by B plus C, if A is 0, then the body will be like this. So basically, we move C to a EAX register. So basically, we move from C memory location to register EAX. And then we add from B location to EAX. So EAX has the result for B plus C. That's a temporary variable. And we move this to A. So back to A. And then we compare if A, but actually we just need to compare this register. If this value is negative, not equal to 0, I'm sorry, not equal to 0, then we will jump to L1. So L1 is here. So this will actually, if it's not 0, we actually bypass, and if 0, we go into body. So here, actually, if 0, you go into body, otherwise jump to L1. So let's finish these two statements. Conditions and branches. So we can write the A less than equal B, then body, or A greater than 0, then body, and at least you can see this, similar to the previous example. ISA make a difference in performance. So in the x86, the code fragment C equal maximum of A and B might naively be translated like this. But if we have a conditional movement instruction, it can become the following. So we can have move under condition. And this one, we don't have move under condition. We have only set a condition and jump. So here we spend 1, 2, 3, 4, 5, 6, 7 different instructions, and we only need 5. So we can say that this with a instruction, we can set 2 clock cycles. Instruction set architecture 2, architecture implementation. So let's draw out this again. We have basic data path, and then we have top line the data path with clock latch, data latches in between the stages. And then we have this super pop line that actually divide each stage into 2. Then we have superscalar that allow multiple instructions to be dispatched at a cycle. Then we have the translation for the command to microcode that allow VLIW and the outer order execution. So they have different data paths. So data paths depend on the instruction level parallelism mechanism you use. Architecture implementation. As technology advances, there are occasionally times when some threshold is crossed that suddenly make it possible to design machine in very different way. One example of such a paradigm shift occurred in the mid-1980s is the development of RISC. And since then, we have been using RISC machine for a long time with the modification we mentioned before, the 4 or 5 different modification. And recently, we have the GPU, graphic processing unit, after that, and now we have the TPU, tensor processing unit. I will mention about this after this lecture. Architectural implementation. During 1950 and 60, the instruction set of a typical computer are implemented by sorting together a large number of discrete components. And then we have the VLSI. And because of the VLSI, we have the RISC machine. Before that, it's all discrete components. And to build a faster computer, one generally design extra more powerful instructions. So at that time, people like to use powerful CISC. And after VLSI being available, people start to think about RISC machine, put everything on chip. Before that, is trying to provide more instruction, more powerful instruction to do computation in shorter cycle. And then because the instruction set grow too much, then the assembly programming is become a difficult thing to learn. And architectural implementation. IBM hit upon the implementation technique called microprogramming, and after that, the microprogramming is invented. Even today, for the microcode, is following the idea of microprogramming, and microprogramming made possible for instruction to have a different level of decoding. So there's a basic idea is to build a micro engine in hardware that is execute and like an interpreter program in the firmware. And more expensive machine have fancier micro engines. That's back into like 1970s, 1960, 1970 for IBM 360. And after that, people explore the possibility of using RISC. And then until 90s, to start to think about using a microcode again to do pipelining. Architectural implementation. Microprogramming make it easier to extend the instruction set. People ran study to identify instruction that often occur in sequence and update bookkeeping information in the step. Then provide new instruction that perform the function of the sequence. Okay, this is actually some history. Architecture implementation. The microcomputer revolution in late 1970s occurred when it became possible to fit micro engine into one chip. Then at that time we called it microprocessor. Before that, it's a firmware of chip. So microprocessor is named because it had that micro engine, on-chip micro engine. And mid-1980s, VLSI technology reached the point. Then it eliminated the need for micro engine and implement the processor on single chip. And then it's the invention of RISC. But later the microcode being used as a instruction interpretation again, then it become the our order execution and VLIW. Architecture implementation. With hardware-only processor on chip, it then became possible to apply certain performance enhancement trick to implementation. Okay, then it's the revolution by RISC. The philosophy is give up nice and fancy features or instructions in order to make common operations faster. That is actually unify the clock cycles. Don't put a longer clock cycles. RISC machine, a common misconception that is a small instruction set. Okay, the early days of RISC machine is actually really small instruction set, but later it got expanded. So RISC machine should be viewed as a machine in which at least one instruction can be started every clock cycle, and actually it's optimized. It's an optimized CISC. All possible mechanisms have been employed to minimize the duration of the cycle and maximize the number of functional units that can be operated in a single cycle. So basically try to minimize the cycle time and maximize the number of the functional units that can be operated in parallel. That's the design for RISC. Architecture implementation. Reduce cycle time comes from making all instructions simple and regular. Try not to invent too complicated instructions that may not be able to parallelize with other instructions. So simple instruction set never have to run slowly because extra logic or extra memory access. Maximum parallelism comes from given the instruction as very regular, predictable format. Compiling to modern processor, pipelining. Now this is more related to our programming language. Basically, the execution of the pipeline instructions are this. We have instruction, fetch, decode, execute, and store or write back. And we pipeline like this. And to compile to modern processor, the processor has to be careful not to execute an instruction that depends on the previous instruction. So try to minimize intermediate data dependency and try to minimize the store. The store is like some instruction waiting for some result to be ready before it can be executed. That we call it a store. So store is a pause of the pipeline. So the pipeline will stop. So basically this is running, instruction, so maybe some of them stop. If this stop to request for some data to finish, then this clock cycle will keep going on until here to resume. So some other instruction will just hold, and like this. The execution will become like this. And then we will lose a few clock cycle that actually waiting for memory in here. Try to minimize the store or eliminate the store. Compiling for modern processor. Low and low delays are influenced by dependencies. There are three types of dependency. Flow dependency, or called control dependency, anti-dependency, output dependency. We will explain these. Branches and branch you may predict well. You may go to one way or the other, but this may also waste the cycle times. So now let's look at the flow dependency. What is flow dependency? If my result from statement 1 is needed by statement 2, now we call it flow dependency. So this A won't be ready if the S1 is not completed. This one is really bad, so this one definitely need to be avoided. And this one, we fetch data, but this one cannot finish before this G. Okay, so you have the instruction decode, instruction fetch, instruction decode, and then execute. And then you have memory fetch, memory cycle, and then write back. So this one actually get the data at this stage. And some other instruction. The next statement 2 maybe is instruction fetch, instruction decode, and then here this one will have execute, and then it will also do and then finish by write back. But everything can be done in register. So if this class cycle made longer, then this one cannot jump ahead too much because there is a anti-dependency. But this one is not as serious as a flow dependency. So flow dependency is a true dependency, and anti-dependency is a dependency. If you want to do out of order execution, then you cannot jump too far ahead. So you probably can jump 1-2 cycles, but not too many. There's a limitation for out of order execution if there is anti-dependency. So here is the dependency chart. So if we right here we have add S2 and register 2 and register 4, and then we set the RS ready to write back, and this RS need to wait until this stage to be finished. So that create bubble. This type of delay we call it bubble. Bubble is that you wait for the result to be finished. And store is different. Store is you have the memory access cycle here is start by itself and make it longer until you can do finish OS. And then the next one continue to waiting on it. So this one called store if you have memory access and take too many clock cycles. And this one is created as bubble because you wait for previous pipeline stage to be finished. So there are two terminology. One is bubble, one is store. They have two different meanings. Control dependency. The previous one we have flow dependency, anti-dependency, and this one is control dependency. Control dependency means I continue to execute my instruction 1, 2, 3, 0, 1, 2, 3. I finish here, but I see a branch. So I may go this way, I may go this way. Then what can we do? We can predict whether it's true or false, or we have two processor units to one execute true, one execute false. And then once we know the result for the decision on this node, we squash the part that's not useful. So there's a branch detection or branch squashable instruction to minimize the penalty. A branch detection is based on previous execution result. Say maybe 90% we go this way. So we just run this, and if not true, we roll back. So that actually there may be some branch prediction can be used. So compilation for modern processor to minimize the store is the worst, and then also try to reorder all those instruction to minimize the so-called bubble as well. So low and branch take longer than ordinary instruction. Low have to go to memory, which is slow. Branch disrupt the pipeline, and processor have interlock hardware. Early RISC machine often provided the delay slot for second cycle of load and store instruction, that's delay slot or bubbles, during which something may occur. The instruction in branch delay slot get executed whether the branch occurred or not. Compiling for modern processor, the instruction is a low delay slot can use the loaded value. As pipelines have grown deeper, people have generally realized that delay slots are more trouble than it is worth. So actually delay slot is not a good idea. Modern processors implement interlock all loads, so you don't have to worry about the correctness issues of load delay. Some machines still have branch delay slot. Later implementation usually provide nullifying alternative that skip the instruction in the slot if static branch prediction is wrong. So it's can be give up or rollback for parallel processing of two branches if the prediction is wrong. Compiling to modern processor 2, RISC versus CISC. Okay, we have CISC and RISC. Unfortunately, even this start a new instruction cycle characteristic of RISC machine is inadequate. In all honesty, there is no good clear definition of what RISC really means. Most recent RISC machines are so-called superscalar implementation that can start more than one instruction per cycle. And if it is a CISC machine, the number of instructions per second depends crucially on the mix of instructions produced by the compiler. So the megahertz number or gigahertz number give an upper bound of how many instructions you can do. If it is a multi-used processor like Power PC G3 and Intel machine since Pentium Pro, the upper bound is higher than the megahertz number, but this is all-day data. As technology improves, complexity is the beginning to creep back to RISC design. But actually right now we utilize more processing units and better memory units and larger cache. Vector processing. If I have scalar processing, I have A1 plus B1 equals C1. So this for loop, I need to finish in n cycles, in n statements of n iterations. But vector processing, I can basically do this. But actually this depends on how many processing units I have. So actually the number of cycles you need is actually this n divided by number of processing units and take seeding function. That's the number of cycle needed if you use the vector processing unit. Compiling to modern processor, we also see CISC machine with RISC type subset. So later we have this, and this is already old. And then actually recently we had the microcode design, so CISC look very much like RISC now. And in a sense, code for RISC machine resemble microcode, and recently we do have the microcode for our older execution and VLIW and superscalar. Okay, so these are all. Compiling to modern processor units. We have basically we need to have an integer processing unit or instruction unit, usually called IU or IPU. And then we have the floating point processing unit, graphic processing unit, vector processing unit, and recently tensor processing unit. And we have other function unit on chip, such as load store unit and some other units as well. Typically, instruction unit floating point unit, and low store unit are the 3 units needed at least for a processor. Because memory is so much slower than registers, then keeping the right things in the register is extremely important. So what we want to do is we have this data path. We have a register, then we have a cache, and then we have cache 2, and we have main memory, and we want to have like as much percentage of processing between here, so maybe 90% of here, and then there's maybe 5% we need to access cache 1, and then only maybe 3% we access cache 2, and minimize like 1% or 2% for the memory access. Try to minimize the access to the lower memory hierarchy. So register file, in order to make process switch faster, the invention of register file is used to save memory access time and the epilogue and prologue of a calling of a function faster. Circular buffer, circular register file, and it's actually invented. Okay, this is old. Spark machine is really old. We will avoid these old data. So major RISC machine are ARM. ARM still in use. Spark is out of date. MIPS out of date. PowerPC, the A for iPhones. So for iPhone right now, we are using the A10, A11 processor. ARM, we have ARM, and actually A is also related to ARM. We have the Intel i7, i5, and now i8. And comparing to processor number 4, multi-thread and multi-core. Advance in processor technology, faster clock cycle, higher level or instruction level parallelism, speculation, keep the pipeline full, try to do branch prediction or running the 2 branches at the same time, larger cache. And technology, we have pipelining, super pipelining, super scalar vector processing, VLIW, instruction set, instruction translation to microcode, reordering of microcode, renaming of register. These different techniques to improve the CPU processing. And x86 architecture. A processor implement IA32 architecture can be executed in protected mode or real mode or system management mode if we use the 64-bit architecture. A processor implement the Intel 64-bit architecture has a 3 above mode plus the I32E mode, enhanced mode, which has 2 sub-modes, compatibility mode and the 64-bit mode. So the register set for x86 architecture are these, and the name of the register are like this. And the instructions x86 architecture are these. We have integer unit, we have floating point unit, we have this called system instructions, and different other instruction set. And the architecture is like this. We may have 4 integer unit, 2 floating point unit, 3 branch unit, and some low store units. It's a McKinney project. x86 architecture, adjacent memory, we have such scheme. So the little endian scheme is used in x86 architecture. And you can read what are the flags in x86 processor. And this x86 architecture for the errors exception handling. And here I give you the x86 architecture very briefly, and it's covered in chapter 5 text. So you need to download the chapter 5 text for the textbook because it's missing from the textbook. You need to download from our website. So now we finish chapter 5. And as I promised, I'm going to talk about something called tensor processor. Whatever CPU we talk about so far is actually the Neumann processor. Here I'm going to talk about this TensorFlow processing unit. That's for Google AlphaGo processor project, and it's for RNN, recurrent neural network processing. So Google's dedicated TensorFlow processor, that is actually has metal aluminum heatsink. So this is covered by heatsink, and then there is a CPU under it. So it's used for deep learning. We have the untrained neural network, and then we have the deep learning data. So get the data, train the neurons, and then we have the new capability with learned network, and then we do in the inference to study whether the picture has a cat in there, and then we optimize, use that as a training model to train the data set again. That's deep learning. Google's TPU design, so is something like this. We have a PCI interface, and we have this so-called host interface, and then here's a unified brain buffer and systolic data setup. Systolic means like what's systolic? Systolic is like blood pressure, right? So it's the pump data actually like a systolic way. Usually it's like I have data pumping this way and the other one pumping this way. So going like this to do some machine type operation. That's a systolic data setup. And then we have an accumulator layer, and then continue. So this is the TPU design, tensor processing unit. But what's tensor? What does tensor really mean? We have 1D vector, 2D matrix, and any data structure higher than 2D called tensor. Or we can even call 1D and 2D as 1D tensor, 2D tensor. So that's the tensor processing for ND array. ND array is tensor. And tensor is the data we process with the TPU. And Google is not the only company who is developing this type of TPU. We also have NVIDIA, we also have Intel, several different companies. This is a PC board for TPU. There are some memory maybe, and there's a TPU inside here. And as I mentioned, the aluminum cover on top of it is the heatsink. If you look at this, is on top of it is a heatsink. So benchmark performance, if we have a compared TPU with NVIDIA, it's actually, you look at the total gigabit byte per second, the die size, the power consumption is way lower than others. Number of Tera operations is way higher than others. And the dies and on-chip memory, these are the benchmark comparison. So the comparison of the TPU with CPU or with GPU, as you can see, the performance is always higher. And here are different benchmarks to be run. Okay, thank you for chapter 5. And this video being divided into 2 parts. I will assemble them together into one file. Thank you. Bye now.